Hey, what's up? Thanks for coming back. This is the final part of this gradient descent series. I know this has been a very long series, but we're going to go ahead and just do the final explanation so that we can move on to the next section of this series. So just a quick notice before we get started. If you go and check the comments, the description for this video rather, you'll see that I've added a new link, a new resource link, and that link is going to send you to this page on my LinkedIn. On my LinkedIn, I've posted the Jupyter notebook as a PDF basically, so that if you're wanting to follow along or to do all the stuff that I did in the study session to get up to this point, all you have to do is just go to that link and you'll be able to look at this PDF and you'll be able to at least follow all of the things that I did in order to work out, what a gradient function is, what it looks like, how to plot it on using matplotlib and all that kind of stuff. So that's the newest update. As I've said in many of the videos before, my resources section of these tutorial and study session things in this playlist, it's going to be continuously built. Eventually I'll probably get like some type of link collector type of thing specifically for this, but for now just keep checking those resources. I'm mostly focusing on posting things that are free, that are just existing out on the internet. Another great source that's on that list is the Machine Learning for Humans, which is a PDF book that you can get for free. And then also the PyTorch resources. They're not necessarily exactly what I'm doing here, but if it's like another way to get into doing some AI work. It's more of the deep learning stuff than it is machine learning. Deep learning is by some accounts considered a subsection of machine learning. So yeah, check those resources. And also, if you have things that you think should be on this resource list, I want to just build the best resource list so that people can like just do this stuff for free. Eventually I think knowledge should be free, and I'm trying to make this series a free resource for people who want to get in, get in and get involved. And also I want to make some resources so that you can have things other than just my videos too. So anyways, that's what I wanted to tell you. Go check that link out. On my LinkedIn, by the way, I post all of these videos on here so you can see them easily. I post a lot of stuff that I don't necessarily mention on my YouTube channel. So my LinkedIn's kind of like the first stop if you're wanting to get some information about what I'm working on and what I'm doing. So I'm going to be posting there before I post anywhere else usually. It's my main social media. So yes, feel free to add me, feel free to follow, all that kind of stuff. Or if you don't want to, that's cool too. One update with regards to like my development environment. If you checked out the previous videos, you saw that I was doing all of my Jupyter Notebook stuff using the Conda web app. I have since switched to using VS Studio Code, which is a much better mentions that will be helpful if this is what you want to do. VS Code is pretty good at like kind of sensing what you're doing. The biggest thing is once you get VS Code installed, just open up the folder or the workspace that has your notebooks in it. And then it'll give you a little message down here at the bottom that'll say, hey, I see you're working in a Jupyter notebook. Do you want to like get the extensions that are appropriate? In addition to that, I'm using IntelliCode. Here are the Jupyter notebook things here. Basically all you really need is just Python and then Jupyter notebook. And then you want to make sure you have some type of environment. I'm using the Conda based environment that I set up, but that's neither here nor there. You don't need to do any of this. You can really just use the web app. The only reason why I switched to using VS Code is because I've been a developer for about 5 years. This is my 5th year. Yeah, October is gonna be starting my 5th year. So for me, I just need to have access to more things. It has a built-in terminal that you can get down here. I like all of that. It's just really nice. And then the other thing is I like to have auto completion. Right now I'm using Copilot, which I'm going to turn off right now. I'm going to turn Copilot off because I don't want to have easy mode. I want to force myself to really know what I'm doing and to force myself to really think through. So I'm gonna turn Copilot off for now. I'm gonna do a video on Copilot, but it's not gonna be in this playlist. If you want to see that sooner than later, let me know. Otherwise, I'm gonna wait, take my time with that. Okay, so without further ado, the purpose of today's stream is to just review gradient descent. I'm not gonna take forever, even though I am long-winded. But I'm just gonna try to get through this because I think I've done enough videos up to this point where if you've been watching those, hopefully it'll make sense. This video right now is really just meant to kind of be an overview so that you can get the gist of it and kind of understand how these maps you to find the values of your parameters for the weight and the bias when you're doing a linear regression. Now, gradient descent can be used for other models, other algorithms, but we're talking about this specifically in terms of univariate linear regression, which means linear regression that has a single variable, a single x value, a scalar value. And the problem with doing linear regression and understanding the cost is that without this gradient descent formula working, we have to manually tinker around to find the best weight and the best bias. And that comes to find the best line. It could take, way too much time. So this gradient descent summation of the difference between the prediction and the target squared multiplied by 1/2m. And then that is what we're doing the gradient descent against. So whatever that formula is for the cost function. Okay, so the goal is to achieve the local minima. So as I mentioned, the lowest cost can be potentially more than one thing. When you get to more complicated functions beyond linear regression, you could have multiple different costs depending on where you set and start your initial values for your weight and your bias. And so what we refer to is a local minima. And for linear regression, it's always going to be a singular local minima, but for other functions in the future, there could be potentially multiples of them when you're doing the automatic cost analysis with the gradient descent. So for gradient descent to happen, we have basically two formulas here that both need to occur and update simultaneously. The first formula here is the iterations. These are iterations, by the way, over our weight and the bias. And so as our gradient descent happens, we're basically updating the weight and the bias here. And the update for each of those has to occur simultaneously because they're interdependent with one another. The weight, for example, is going to be a variable that is included when calculating the gradient, and the value of the weight is being used in the bias when you're calculating the bias's gradient at each interval. So these two need to be updated at the same time. So we're going to talk about these separately, then we're going to talk about how they work together. So first, the formula I'll just explain what this means. So in plain English, what this is saying is at whatever step of the iteration, because it's going to exist inside of a loop, the weight is equal to the weight minus some alpha value, which is multiplied by the derivative of the cost function with regards to the weight. And similarly, at whatever step of the iteration, the bias is going to evaluate, it's going to in this case, this equal signs, this represents assignment. So the bias is going to be assigned to the value of the bias minus some alpha value multiplied by the derivative of the cost function with regards to the bias. And so when I say in regards to the bias, in regards to the weight, these two formulas here are like shorthand and they look alike, but when we're talking about in regards to the weight, in regards to the bias, they're actually slightly different formulas, and we're going to talk about that in just a second. So the notes here on the comments on the notation here, try to make this a little easy. We're iteratively reassigning the value of W by subtracting some amount from it. This alpha is some number that you have to choose. This number can be whatever number is appropriate, but when you configure an alpha value, you have to pick a number that is going to basically help your algorithm converge towards the lowest cost. And if the number is not the right number, then this will not work at all. And this alpha is going to be the same for both of these formulas, for both these gradient formulas. That alpha is also called the learning rate here. And this is going to determine the size of the steps for each iteration. And this will make more sense when we get into the graphic depiction of what this gradient descent looks like. But if you just think about the word gradient descent and how we talked about this bowl shape, either this soup bowl shape or this upside down inverted, I think it's like a logarithmic parabola. I think that's the term for it. Don't quote me on that. Don't quote me on that, but it's like an upside down U shape. As we're moving towards that, the center of this upside down parabola, at the center of that, that's the lowest cost, 0. And so what we're doing with this alpha value is we're changing its value, and that's going to change the size of the steps as we move towards convergence at the center. And like I said, it's going to make more sense when I show you the graph. This part here, I'll make this bigger too, my bad. This part here where it says like alpha times the derivative, this little symbol up here, this looks like a D and then over a dw. This is just like a way to say derivative. This is actually as a partial derivative, but sometimes you could see it as just a derivative. But this derivative is going to be in relationship to the cost function. So just remember when you see these two together, there are other ways that this gets represented. I can show you the other way that you might see this. Let me see if I can find it here. I know there's like another way that sometimes people, I don't have an example here, but there's multiple ways to communicate this. Sometimes you'll see this derivative portion here and then like this cost function. Sometimes you'll see them like kind of collapsed into like a single like little mathematical symbol thing or whatever. I have them separated out. But just know that there's more than one way to present like this part here. Okay, so similarly, these two formulas are saying the same thing, but they're going to look different. So for the gradient descent algorithm, we're going to repeat both of these steps here, boom and boom, boom and bap. We're going to repeat both of them and then update them together at the end when both of them have ran at that interval, right? And we're going to do this until the algorithm converges or until it reaches the local minimum. The local minimum is the lowest cost possible for whatever our alpha and our weight and our bias are, the initial values for them. And the lowest cost is not always going to be 0. Likely it will not be 0 the more complicated and the more irregular your data, the less linear your data is. So both parameters always need to be updated at the same time. Since the two formulas use the weight and the bias, these need to be stored in temporary values before updating so as to prevent premature overwriting. Now here's an example of the wrong way and the right way to do this. And the way that I'm going to show you in the code, this will not be an issue because it will not make sense to do it any other way than the correct way when we're doing this in Python. But just as the kind of an example of why this is important to do them at the same time, you can see here how even though we're doing separate gradient functions for the weight and the bias, both of them are going to use the weight and the bias as some type of variable within them. So if we don't update them together, then these two formulas will not be doing what they need. They're not going to be doing a gradient descent. It's going to be like some whole other thing. Which I don't know, there's like some other things that you can do without simultaneously updating them. That's just not the point of this. So just know that if they're not being updated simultaneously here, you're going, like in this example here, you can see how we're doing the cost, we're doing the gradient function here, then we're updating the weight, and that weight is being used in the gradient function for the bias, and it's already been changed. And like, we don't like that. That's not good. That's not Gucci. That's not Prada. So, so we got to do them at the same time, basically. Just remember that. Update simultaneously, okay? So we're going to be repeating both of these until convergence. The learning rate, which is alpha, controls how big the step is when you take when updating the model parameters, because we're taking the product of the learning rate times the derivative of whatever our cost is with regards to either the weight or bias. So that alpha is going to be multiplied by whatever that derivative is. So the derivative is the slope of a curve, a point on a curve. Just remember that when you're talking about derivative, we're looking at a point and we're like trying to understand how this point is changing as it's moving in this space. And so we describe it as being a curve, like a tangent along a curve. And this tangent along the curve is going to have a positive or a negative value, which is going to indicate which direction it is moving in. So if it's a positive, then it's moving like up. And if it's positive, it's moving like in one direction, like a negative slope or a positive slope. So this is a positive slope. I said moving up, but this is a positive slope. So it's like, it's like this angle is a positive slope, and this angle is a negative slope. This angle is a negative slope. So you can see here, alpha is always going to be a positive number, but your derivative can be positive or negative. And so depending on whether or not your derivative is positive or negative, it's going to give you a positive or a negative product when you multiply by your alpha. And that's going to determine the slope of your line, negative, positive. All you have to remember is that your positive slopes, if you have a positive slope, which is going to be this portion of your formula here, when your slope is positive, it means it's moving toward, your point is moving toward the lowest cost. And that's a good thing, right? Same thing with if it's a negative thing, then it means it's moving towards your cost, just from the opposite, lowest cost, just from the opposite direction. That's a good thing as well. Now, what you would not want to have is you would not want to have a point that is moving like away, because that's called divergence, and that just means that your alpha value is not correct. So key takeaways for this section is that your alpha value is going to have influence over the size of the steps. The size of your steps need to be small enough for you to not overstep your lowest cost, but they also need to be large enough so that it doesn't take forever for you to get there, because if it takes too long, that means you have more processing, more time, more resource intensiveness involved. So when a point along the curve of the cost function has a positive slope, the gradient descent is moving in the negative direction or towards the right side this way. My directions are like opposite from the camera, so I get a little confused here. So it's moving this way. And then when your point along the curve for the cost function is on a negative slope, then it's moving this way towards, so this is my left here, which is your right. So it's moving this way, okay? Just look at this. Just look at this, okay? Just look at this, okay? This top one right here, this is the positive one, this is the negative one. Whatever this says, that's right, okay? Stop looking at the camera. Stop looking at me. Okay, so the learning rate, like I said, is always a positive number, and it's going to be multiplied by some derivative of your cost function with regards to either your bias or your weight, which the derivative is going to provide that negative or that positive. And so, yes, it's just basic algebra. Okay, so we're going to like talk about the learning rate real quick, and then I think after that, we're almost ready to go into the code. So the learning rate, alpha, has a big influence over the efficiency of the gradient descent. When it is too small, then your algorithm is going to be very slow. Okay, it's going to be creeping along. You're going to be hot and bothered. It's going to be overbooked and overly busy. You know, so much so that it probably won't get to where you're trying to get it to go. Okay, and it's going to require a lot of steps to get to local minimum. And just think about this: if you're trying to do this gradient descent over a very large data set, maybe you're doing multiple gradient descents with multiple data sets, and you have limited resources, or maybe you have time constraints over when you need to perform this, such as like live data analysis tools and whatnot, right? If your alpha is too small, you're going to have a hard time, and it's just not going to be performant. But also, you don't want to have it to be too big, too large, right? When your alpha value is too large, it's going to increase the cost potentially, because it'll overstep. Now, this overstepping part, that's gonna make more sense probably later on, but let me just show you really quickly, right? So if you imagine that on this little curve right here, your alpha value is going to determine how far each of your steps are as you move toward the local minimum, right? And the goal is to have an alpha value that is small enough so that as you move along this, you can actually land at whatever the lowest cost is, which it could be 0, it could just be some other small number. But if your steps are too big, your increments are too big, then it's very possible that you could overstep, right? And so like, let's say that your steps are too big and instead of getting to your local minimum, you accidentally overshoot and you end up like here. Well, now your algorithm is going to have to go back in the opposite direction and it might end up over here and it might just continue bouncing back and forth, or it might diverge and like just increase your costs actually. So your alpha value cannot be too large, right? It'll increase the cost of the algorithm and it will overstep the minimum. It'll fail to converge, and in worst cases, it will diverge. And it could have the same long-term implications of being very resource intensive because it will not stop unless you have maybe like some iteration cap or whatever like that, which we will in our case. So when the minimum is at 0, when the minimum is reached, or when it is at 0, what we will notice is that our weight and our bias will stop changing, or the changes will become very, very, very small to the point where they're not making an effective difference. So that's what we're looking for, and that's how we know that our algorithm has achieved the goal, is when we stop seeing those changes happening to the value of our weights and our bias as they're going through the iteration. As gradient descent approaches local minimum, the derivative becomes smaller and the update steps become smaller. You can reach minimum without decreasing the rate. Not sure what I meant here. My bad. I'm just gonna go ahead and delete that. I think that might have been something I was writing and then I didn't make sense. Just ignore me. Just ignore that part of the thing. That did not happen. You did not see that, okay? Got my sunglasses on. I'm too cool to be making mistakes like that. Okay, let's go back to this. Okay, so for gradient descent for linear regression, these are the two formulas. This is what all of this translates out to be, like in a more concise way. Just remember that we have a linear regression model. This linear regression model takes in some input, x, and then it multiplies by a weight and bias. This is what we're configuring. So when we're doing this gradient descent and cost functioning, we're doing it because we're concerned with getting the best setup for weight and bias so that when we pass in some x value, we can make an accurate prediction that is aligned with whatever the training data is that we're using as the basis for our model. Okay, so the cost function here is how we're able to determine the effectiveness and the accuracy, the integrity of whatever the weight and the biases are that we have determined to use for our linear regression. So when we want to know if this whatever weight is and whatever bias is actually useful for our function, the cost is going to be a number, and that number is going to hopefully approach 0 as the gradient descent gives us a better weight and bias to use. But this is the function we use to actually determine, like in any specific instance, how well our linear regression model is working, and that is called the cost. We want the lowest cost. We like it to be cheap. We like it to be potentially free, but hopefully just cheap. Lowest cost. Just remember it that way. The bottom of the barrel prices. Think about the little curve. Bottom of the barrel prices. That's the little mnemonic image that you should have in your head. The lowest bottom of the barrel. Got it. Just the lowest cost. Okay. By the way, if you hear some rattling noises and general chaos in the background, that is my lovely, beautiful tortoiseshell split-faced cat named Clue. Because when I start talking, she gets very hyper, and just know that I do not live in a war zone. Okay, it's my cat. That's just how she be doing. Okay, so now this is the part here where I don't think this matters. This is like some pre-calculus type of things, some pre-calculus type of trigonometry type of things. I'm not gonna bother to try to explain all this to you, but I would just think about it like this. Whenever you're seeing these two formulas for the gradient function for the weight, with regards to the weight and with regards to the bias, just know that these two here, this and this, these are the actual like equations that we're plugging all of these variables into, right? The way that you can get to these is by doing this derivative, which is its own thing. Like a derivative is like a very specific operation that you perform against like some complex number with like coefficients and whatnot. But you don't need to know that. All you need to know is this formula here. But these are the steps that you can do to actually derive this formula that we're using for our gradient descent. But you don't need to know these things, although I do encourage it. But I'm not going to go into that today. So I'm going to just talk about this here, and then I think we can jump into the code, right? Okay, so I have it written out here in LaTeX, so you don't have to look at my weird handwriting. So we're going to talk about the partial derivative for the cost function of j with regards to the weight first, which is this. So just remember, this here is the same thing as this here. Okay, so this here, we're just breaking it down and isolating it so we can understand exactly what that formula expands out to. So with regards to the weight, we're saying the weight is going to be assigned to the weight minus alpha, and this derivative of the cost of the cost function with regards to the weight, that expands out to this. This is a summation. This little sigma symbol here is a summation. We have a maximum and a minimum. The minimum is like, the minimum and maximum determine like our how many iterations we go through to do all of this, and within the data set, what index we're starting with. In math, our indexes are starting at 1. In programming, they start at 0. So here we have I equals 1, but if this was like a loop, right, it would just start at like, if it was a loop over index, the first index would be a 0th index in Python. So what we're saying here is that we're doing a summation. We're taking all of the instances of this portion here. When this portion here runs, it's going to run for each of the indexes that exist within the data set of X, which is the collection of inputs that we have for our model. It's going to basically run our linear regression function for that current index of X, and it's going to which is basically Y. This is going to evaluate out to Y. This is the prediction Y for our index of X, and it's going to subtract from that. It's going to subtract our target value for that same index of Y. This index of Y is our training data, and this here is like our Y prediction basically. So Y prediction minus Y training is going to take this entire thing, whatever this arithmetic evaluates out to, and it's going to multiply it by X at that same index. It's going to do this whole thing for each of the indexes within our X data set, and then it's going to multiply it by 1 over m, and then that whole thing, this whole summation multiplied by 1 over m, is going to be multiplied by our alpha value, and then this whole thing is going to get subtracted from whatever our previous weight is. And this number here, this whole thing here, is going to be it's going to make our weight increasingly small. So when we're seeing this weight is being assigned to this formula, it means that every time this formula runs and reassigns the value of the weight, it's going to be smaller and smaller and smaller and smaller and smaller, but it's going to get smaller in a non-linear way. Like a linear way would be like the number 10, and then each step it gets 1 smaller, so 10, 9, 8, 7, 6. This is not that. This ain't that. This is something else. This is a non-linear decrease in the size of the value of W, which means, like, for example, it could be like one step it might be -1, the next step it might be -0.8, the next step might be -0.5, and just like that, it gets smaller but in a non-linear way, because as we're moving toward the lowest cost, we want to edge up, we want to approach it. We don't want to overstep it. And so in order to make sure we don't overstep it, the steps need to be just increasingly smaller, okay? And we're gonna see how that works out on a curve. And the other thing here is like the derivative of the cost function for J with regards to the bias, very similar. The only difference is that we do not multiply this the steps of our summation by x at the index. We just leave it as the prediction minus the target. We don't do this x to the index product at the end of it. Otherwise, everything else is the same. Now, I'm not an expert at understanding exactly why these two things are different. Sorry. One thing I can tell you though is that when we're doing the way that the weight and the bias are used in the linear regression function, the weight is multiplied by our x value and the bias is added to the product of our weight and our x value. So, you know, I would encourage you to look into that. I think that has something to do with it, but I'm not going to try to act like I know the exact answer. So sorry about that. Okay, so just remember that this FWB right here with the x to the index, this is just a shorthand way. Well, it's not really shorter, but it's just another way to say our linear regression function as it's being used to make a prediction. And the other way to describe this is to just call it y. And then we're updating our weight and our bias simultaneously. I'm going to show you that here in the code. Leads to a local minimum, not a global minimum. And then depending on where you initialize your weight and your bias, there may be different local minimum. Not necessarily for linear regression, but you know, in other types of algorithms, that is certainly true. For the squared error cost function for linear regression, there will be a single global minimum, which happens to be the local minimum. This cost function is called a convex function because it is descending down a convex curve. Okay, so when we're running this, earlier I was saying like we're going to, what was it? Here I was saying that, okay, I said we're going to repeat both of these costs, or these gradient functions rather. We're going to repeat these until they converge. There's a name for that. The repeating of it until it converges is called batch gradient descent. Each step of the gradient descent uses all the training examples at each update instead of a subset. There's a version of the gradient descent that uses all subsets. So we're using all the training examples at each update, okay? So now I think we can get into the code. These notes here will also be published to my LinkedIn at some point. I don't want to do all like this separately though. What I'm going to do is I'm going to take all of the notes from linear regression, including the cost function and all of these things. I'm going to put these together into a single PDF type of thing, and then I'm going to upload them. So I'll let you know when I do that. I'll announce it in one of these videos. Certainly you'll see it in the links, if not in the actual announcements. So just stay tuned for that, okay? Okay, so now I can just make this smaller and we can go here. Okay, so where are we sitting at? We're sitting at 34 minutes. Okay, what I'm gonna do is I'm gonna take a small, just a teensy weensy little break here, just to go get some water, and then we'll come back and then I'll jump into the Python code here. This shouldn't take too long. Like I said, this exact little notebook, you can just go to the link in the description and see this for yourself. So I don't think I need to go through all of the explanations. As far as like the markdown parts of this, these markdown notes here are basically everything that I talked about in my my little like Obsidian notes here. The big thing I want to discuss with you is to just talk about how this actually plays out with the code and walk through that, okay? So stick around, go ahead and get yourself some coffee or whatever you like to drink, some tea, get your little snack, a little sneaky snack, and then I'll be back in about 5 minutes, okay? Thanks. Okay, let's go ahead and get started up again. I'm back from my little break. Hopefully you got yourself, a little snack or whatever, and you're doing good and doing fine. Thanks for sticking with me. Let's go ahead and jump back into this and try to get this wrapped up so that we can go on about our lives and, move on to other things. Okay, so we're looking at the Jupyter notebook in Python for working out our gradient descent using linear regression. Now, in what I'm doing here, there is a little utility file that has some dependency stuff going on here. You're not going to necessarily have this file. At some point, I'm going to try to make this available. This utility file basically is just providing some things that will help us to plot out our stuff in these little plots here, basically. So don't expect this to work exactly for you unless you have this utility file. If you do take the course, which is listed in the description of the Coursera machine learning specialty course or whatever, it's in the links. If you go there, you'll be able to get this file from their labs. And if you take that course, you don't even need to necessarily do this in your own environment. I'm just a nerd and I want to have this for myself in the future, so that's why I'm doing it on my own separately. So like I said, you need to have this file, and here's like a style sheet. And if you do go ahead and get these two here, just drop them in the same directory as your notebook. So like here and here, basically. Okay, I'm gonna just open up this real quick. If you want to know what's going on inside of this utility file, it's just all this kind of stuff here. It's just some things that make our plotting and graphic depiction a little bit easier, but totally not necessary to understand this. Okay, so our problem statement is the same problem statement that we've been using all along in this. And that problem statement is we're looking at two different houses here, and we're trying to make a model that is going to help us to make an educated guess on what the cost of the house is, given that we know the square footage of that house. So when it is 1,000 square feet, we know that this is our training data, by the way. With our training data, we know that when it's 1,000 square feet, that the price is $300,000, and when it is 2,000 square feet, then it's $500,000. And so between those two data points, we want to build a model that can help us predict some novel input. Okay, so we basically are going to create two arrays. This is the same thing we've done before. Two arrays. One's going to hold our X training data, and one's going to hold our Y training data. The pairs for these, so like each of these rows represent an index. Each of these columns represent one of these. So either the X, the first column, or the Y training data. We're storing these into two separate arrays, basically. But just remember that the columns represent the X training data, and this column and this column represent the X and the Y training data, and then the rows represent the pairs, so the indexes within those two arrays. Okay, and indexes are zeroth indexes in Python. Okay, so the first thing we're going to do in order to start this whole gradient descent notebook is we're going to compute the cost. Computing the cost is simple. Computing the cost is the cost function. So we're defining our cost, compute cost function here in Python. To do that, we're taking in 4 arguments. We're taking in some X training data, and we're taking in some Y training data. So this X and this Y, it's like the complete set of whatever this X train is, and this Y train is. These are both going to be arrays. In fact, I should probably note that here. It's X training data, and then Y is an array. Y train. Oops. Yeah. Okay, there we go. Okay, so these are our arguments, and then actually, you know what I can do? I can just put this in triple quotes. I really should have done this before, but I didn't, so here we are. I'm gonna go ahead and move this inside of my quotes here. Bam, bam. Okay, so these are arguments. Yep, these are arguments. And then the other one is our weight and our bias. These are scalars. Okay, weight and bias. Okay, so remember when we're doing this, we need to have an M, which is the size of our training data, the size of this array. So to get that using NumPy, it's x.shape, and then we're going to put this 0 in here as our parameter here. We're going to set the cost to 0. This cost is going to be a summed value because we're iterating over the entire range of M. So this loop here is our iterating over the entire range of M. The linear regression function is denoted by this f_wb. So we're running the model with respects to the weight and the bias for some index in this loop here. So the linear regression function is weight times x at the index plus b. Order of operations means that this part here, this portion here, this weight times x at the index, that occurs first, and we're going to take the product of that and add the bias to it. And then to get the cost of this cost here is going to be whatever, so this cost is going to be a summated cost here. So for each iteration, we're going to take the whatever the current complete cost is, and we're going to add to that the cost of the well, this is really the cost of the individual iteration. So this is the remember that f_wb, that is our linear regression function. That is the model that is making a prediction based on some index of x. It's the prediction minus the y training, and at the same index squared. And then we're going to do that for each of the indexes. We're going to take this squared cost error for each of these indexes, and we're going to add it to the cost and store them in this variable. After we do that for all of the range of M, then we're going to get a new variable called total cost. We're going to take this entire cost, the summated cost of all of those indexes, and we're going to multiply it by 1/2m, or divided by 2m. It's the same thing. And that's going to give us a total cost. That's going to be the cost, the total cost for the current weight and the bias that we're working with for our entire data set is going to be represented here as the output of this function. Okay, so that is this is like a core formula. This is going to be reused every time we want to determine the cost of some weight and bias that we are working with. We're going to run this function. Okay, so gradient descent, we talked about this earlier. Here are the formulas just for like our own edification. Now remember, we just did this compute cost here, the squared error cost function over the range of M for the indexes of our X training data, which returns total cost. We need to have 3 functions here for this to all work, for this to all mesh and gel and, like, you know, be all Gucci and everything like that. We need a cost. We need to compute the gradient. We need a compute cost, and we also need a gradient descent. Gradient descent is going to basically take. It's going to basically take our compute gradient and our compute cost, and it's going to do it towards the ends of achieving a minimum, a local minimum. Okay, so the next thing we need to do is this compute gradient. Compute gradient is going to take in the same the same arguments, these same arguments that we use in compute cost, we're also going to reuse them in compute gradient, okay? Here. And remember that this compute gradient, the whole purpose of this is to get the derivative for the squared error cost function with regards to the weight, and to get the derivative for the squared error cost function with regards to the bias. And then to spit those out as the output of this function, okay? So it computes the gradient for linear regression. Our arguments are going to be the same. I don't have to explain these again, but returns scalar values for the gradient of the costs with regards to both the weight and the bias. So I'll type it in. So to start this off, we are going to get the size of our training examples. Same thing as before. We're going to store that in M. For our summed gradient cost for the entire training set, we're going to start off with these two derivatives as being set to 0, because we're going to add to them at every step in our loop. So we're going to loop over the range of M, and then we're going to do some wizardry and everything, and then we're going to take whatever we get as the output of this, and we're going to store that in these two derivatives with regards to, you know, whatever they correspond to, the weight or the bias. So first things first is we're going to have our linear regression model. Now this linear regression model is being explicitly written here, but this is literally the same linear regression model as this. They're the same because linear regression, the linear regression formula is the same, and we're using the same weight and the same bias, because here and here and here. So this is the same thing. This is the linear regression model as applied to whatever the index of x is. The same things we did before. Next thing we're going to do is we're going to calculate the gradient cost for an index. Okay. So gradient cost for indexes, we're going to store these in temporary variables, because remember, as I was saying before, we have to update these these summated gradient costs. We have to update them simultaneously. We have to update all of this simultaneously, and we just don't want it to be weird by not doing it that way. So we're going to store it in these derivatives with the underscore I to denote that. So here, this is the linear regression function. This is the prediction minus the target, both at the same index. This is taking in the x, and it's going to spit out some y prediction, and it's going to subtract from that the target, and then it's going to multiply it by the x of whatever the index is. That is the derivative of the cost function with regards to the weight. And then the same thing for regards to the bias. The difference here is that for the weight, we're getting a product of that times the x at the index, and for the bias, we're not going to do that at all. That's the key difference here. Okay. So this is doing this for every index, and it's going to store every index of this in a temporary variable here. Okay, and then it's going to add that variable to the summated gradient cost. So each of the weight and the bias is going to have its own variable. It's going to store them as this goes on. And then after this occurs for the entirety of the range of M, so for all of our training data, then we're going to take these two summated gradient cost scalar values here, and we're going to divide them by M. And then that is going to give us the final thing that we need. It's going to basically give us a value at the end that is the gradient cost with regards to the parameters, but like for the complete set. It's going to be our batched gradient cost, basically. Okay, so how does this look when we depict this in our graphic here? Now this is before we do the gradient descent, but we're going to talk about how this looks graphically here. So remember that we have some things going on that are being provided to us by our lab utility. Let's see, I can probably even pull it up here. Here, this is what's going on here. You don't need to know this, but just know that there's some wizardry that's enabling this plot to occur. All you need to know is that what this first on the left side here, what this is depicting is along this x-axis, these are changes in our weight. This is assuming that we are doing this gradient cost stuff, gradient cost and gradient or compute cost. Assuming that we're setting our B to be only 100 and to not change, this little plot here is only depicting changes that correlate between the weight and the cost. Okay, so we only have our weight along the x-axis here. Okay, so when our weight is at 100, then our cost is going to be here. When our weight is at 200, our cost is going to be at the 0. And when our weight is at, let's see, 300, then it's going to be here. This is the negative slope, this is the positive slope. Okay, and this is the local minimum. And then for linear regression, it's also called the global minimum. This here is called quiver plot. These arrows, the longer the arrows, the further they are away from the local minimum, and the smaller they are, the closer they are to the local minimum. And so basically here, this is just showing you similarly what's being shown over here. I don't like the quiver plot, so I'm not gonna talk about that. This is really the thing you need to know, is this here. But this quiver plot is depicting the relationship between the weight and the bias, as if both of them are changing. Okay, so let's see. I have some notes here. I guess I'll go over them because my notes do explain this quiver plot, which can be a little bit confusing. But I'm gonna start with the left one first. So this shows the derivative function with regards to the weight only. The slope of the cost curve related to the weight at various points. Derivative is going to give you a slope along the curve. Depending on the weight, the slope can be either positive or negative. The derivatives will always attempt to converge at the lowest cost. The lowest cost is down here at the bottom. This at 0 is the lowest cost. And we know based on this graphic depiction that the lowest cost is going to be achieved when the weight is 0 and when the bias is 100. And you can see here in the code here, we are fixing the bias here at 100, just for your insight there. And then on the right here we have this quiver plot. As the gradient function runs, the gradient becomes smaller based on the alpha. Okay, the direction and the slope of the arrows reflect the ratio between the two gradient functions for the weight and for the bias. So this x-axis is the gradient function for the weight, and this x-axis is the gradient function for the weight. This y-axis is the gradient function for the bias. The gradient points away from the minimum, and the scaled gradient is subtracted from the current value of weight and bias. What does that mean again? I can't remember what I meant when I wrote that. Give me a second, y'all. Stop judging. Stop judging me. I'm trying to remember. Okay, so what this means, like, you know, I was saying earlier that there is like no single best weight and bias. Because of the way the formula works, like you could have different combinations and potentially achieve the same. You could potentially achieve multiple different combinations of weight and bias. That's what this is showing here. So it's just saying here, like, there are all these possibilities that you could use to approach the lowest cost. And basically this, if you were to imagine that there's like a diagonal line that's going through this portion of the plot here, these are the different combinations. So like right here, weight is, when the weight is 0 and the bias is 100, like this right here, this little tiny point, you probably can't even see it. This correlates, this point right here correlates to what we're seeing here. But if you were to put in like these other combinations, like a weight of, looks like here is maybe like 375 and a bias of negative 200, like you could also achieve like a minimum by doing that as well. So basically this is just saying that there are multiple, this is a multi-potentialite type of formula, and any of these could potentially suffice. And what makes the biggest difference is what you initialize your weight and bias as when you start to do your gradient descent. You know, whatever you initialize your values as, in this case we're initializing them at 0 and then proceeding forward. But if you initialize them at a different number, then you could get like different results. But the key thing is that you just want to achieve the lowest cost. And the gradient descent is what will help us to understand what that actually looks like. So yeah, this is a little bit confusing. Don't worry about this Clifford plot. Big thing is understanding what this is, or the Super Bowl. Okay, so next thing we're going to do is we're going to look at the gradient descent function, which is going to utilize the compute gradient and the compute cost together. And together, these two will be used automatically to give us some output value. And we're also going to be able to track the history and everything like that, so we can see how it all works out. So this is going to perform the gradient descent to fit the weight and the bias. It's also going to update the weight and the bias simultaneously by taking a number of iterations for the gradient steps, and it's going to, at every iteration, it's going to update them, and it's going to use some learning rate of alpha. Here are our arguments and parameters. X, Y is the same. When you see W underscore N and B underscore N, these are the model parameters that we are initializing with here. Alpha, some learning rate, number of iterations. We need to put a cap on this because if we were, for example, to choose the wrong alpha, our process could just continue infinitely. So we need to put some sort of cap on the number of iterations so that we don't use up a bunch of compute resources and whatever. That's really important if you were to scale this up. And then our cost function, of course, and then our gradient function. These are just the two functions. We're going to actually spell these out and store them in. We're going to store these two functions so that we can use them without having to rewrite them every single time, basically. I believe that's what we're doing. Yeah. Okay, so other than that, what we're returning here is we're returning a weight and we're returning a bias. And the weight and the bias that we're returning, these are going to be whatever our gradient descent is going to conclude to be the best values. We're going to just store them in a weight and a bias scalar. And then this J history, remember this J in terms of this represents the cost. So we're gonna create a list that stores the history of the costs as they go through each of these steps. Then we're gonna return a list of the parameters of weight and bias as they go through these iterations. We're gonna store those as well, so basically we can track and kind of see like what this is doing as it goes throughout its whole process. Okay, so the first thing we're going to do is we're going to basically create a deep copy of our weight, our incoming weight here. We do this so that we can afford modifying the global weight. Deep copy is just a way to recursively copy one object into another, basically. And this is going to just set up this data structure. Similarly, this is all just setup stuff. We're setting up a list for both our history. This is our main loop here where we're iterating over the range. Remember I was saying before how we're only doing this for the number of iterations. So in this case, we could do like 10,000 iterations. We could do like 100 iterations, but we're only going to do that. We're not going to let it just keep running and running and running because it'll never stop. Basically, it'll never stop. Now, even if it gets to the lowest cost of 0, it's going to keep going and the values are just not going to change, but it's going to keep trying to run it. So we need to have some stop condition. You could do that in other ways too, but we're going to do it this way. So we're going to calculate the gradient and update the parameters using the gradient function. That's the first. Let's see, 1 second, sorry. So this is the gradient function is this here. So when you see gradient function, just know that it's actually referring to this compute gradient. It's the same thing. We just have a different name for it because this is occurring inside of this function here, but this is the same thing as this compute gradient. So we're taking it in as a variable here, and we're passing in the arguments here. And remember that when we do this compute gradient, it's actually giving us these two derivatives, the derivative of the cost for the, with regards to the weight, and also for the bias. That's what we're destructuring off of that here. And we're using the xy and the weight and the bias that we're getting in for this function here. Okay, so when you see here, this is using weight and bias, that's being set here. Okay, so once we get the two derivatives from this gradient function, we're going bias, and then this is with regards, ooh, looks like I cut out for a second. Sorry about that. Are we good? Okay, I think we're good now. Sorry about that. I think I cut off there for a second. What I was saying is these two, this here and this here, these are the two gradient functions, the gradient descent functions. And the first one is for the bias. We're utilizing this derivative function, same as here, and we're utilizing this derivative function, same as here. Both of these respectively are the weight and the bias. Multiply, we're getting the product of those by alpha, and then we're subtracting that from whatever the bias was. So remember, because we're doing this as a loop, these biases and these weights, these are summated values that are being, actually they're not summated values, they're, what am I trying to call them? They're like placeholders that are being manipulated in a mutable way every time this loop runs. And so we're just updating these, and we're updating these at the same time. We're updating these at the same time. This is after we've done our derivative stuff. But before I was saying, if we don't update them at the same time, then our formula is just not going to work, okay? So this right here, this is the core thing that we're concerned with here. This is the core thing we're concerned with. One second. Okay, so what we're doing next here is we're going to save the history of our cost for each of the iterations. Yeah, we're saving the history of our cost for each of these iterations here. That's what this J_history is. So what we're gonna do, and maybe I should actually just show you really quick. We're doing 10,000 iterations, but we're going to basically do them in sets of 1,000. So what this saying right here is for every iteration before we get to that 10,000, we're going to append into our cost history and our parameter history. We're going to append whatever that little subset is into those two lists. Okay, so for the cost history, we're going to run our cost function with our arguments. This would not be like truly necessary, by the way, but this is just going to be nice for debugging purposes, for us to actually see what's going on. And we could also take this historical data, and we could also diagram this out on the plot as well, which is what we will, I think we will do in this. There should be 10 of them, and we're gonna print all these out so we can see them. So that's what this code is doing right here. We're gonna do this inside the loop. So comments on formatting. This is a sidebar. I have just a quick side note. Where did I put it? Where did I put it? Here it is. Okay, so for Python 3, I don't know exactly what version of Python 3.6, we're going to be using this string formatting like this style with the F and then the quotes and then, you know, your actual string. This is the style that we're using. So if you're not familiar with this, it might be a little bit confusing. This is super easy to look up though. Just if you go to YouTube and type in Python F strings, then you'll be able to kind of get a little information about how this works, because it could use, and then we're going to get the weight and the bias as well. And this is for each of the iterations grouped into thousands, which will give us 10 sets. When you see, or how should I start this? Okay, so I'll start it like this. Here you see the cost is one of the indexes from our cost history list. This -1 here, this just means that we're going to take the last cost in that array. We want the last thing in that array for the current iteration. So like if our array has like 100 things in it and we're about to print off a group that represents the first 100 things in that list, we only care about the last one because that last one is going to represent the cost for everything before it. So that's why we're getting the last thing off of there. And then we're this colon 0.2e. That's just a way to format for scientific notation, which reduces the number by making it into like something with an exponent or a logarithm. So basically, just to know that this -1 means to grab the last item off of a list, and this 0.2e, that's a way to format. Section is just going to be, the iteration, but this :4, that's just padding. We want our numbers here to be lined up on the right side, so 4 just means that we're padding it with 4 on the left. See here. So none of this is like truly necessary, but it is nice if we want to see this in our console. The big thing to know is that for the iterations here, we're doing our gradient function, we're updating our parameters, and then we're going to spit out whatever the gradient descent determines our best lowest cost weight and bias is by doing that gradient descent. And this also gives us the history for both our parameters and our costs. Okay, so this right here is us actually running this gradient descent here. This right here. This is us actually running it with our training data, with our initial weight and bias, with some alpha value, which we have determined here is going to be 0.01. This is in scientific notation, 1.0e to the -2. This is, you want to know what that means, all you got to do is just put it in your console and it'll spit it out for you. It's pretty straightforward. That's what I did because I do not have the mental facility to get to get all that information just from my own head. I ain't really got it like that. So yeah, just remember you could do that. We're going to run our gradient descent, and then from that we're destructuring these 4 values, which are these. It's 4 variables, not values. Okay, and then we're going to print off the final weight and the final bias, which is this and which is this here. This this iteration is I, so this is indexed 0 indexed, so it's going to look like it's offset by -1000. Just know that this is the first 1000. Oops, this is the first 1000. This is the second 1000. This is the third 1000. It's just the indexing is 0th index. On that array of history items for cost, that's what this is here. Okay, and then the scientific notation, you can see how it's been reduced to something that can be communicated with exponents. So the cost starts very large and rapidly declines as described in the lecture. That means that cost is very expensive. And then as we go through this process, this cost in this column here is going to become smaller and smaller and smaller as it approaches 0. And even though, like, so right here it says 7.93 to the 4th, and then 7.93 to the 1st, you can see here that we're actually switching here. So instead of doing the exponents, we're like doing, I don't know the word, I need to figure out what the word for that is. Like, what's the opposite of exponent? Let me look it up. The root, the rootedness. It's the inverse operation of an exponent. I'm just gonna call it that. if you got this far, you probably know what I'm talking about. So I'm not gonna worry about it too much. Sorry. But yes, basically what the key thing here is to be by some order of magnitude. And then when it's a plus, it's going to be like, it's going to be, it's going to have an exponent of that number, which makes it larger. So these numbers are becoming smaller, and they're becoming smaller as they approach the local minimum. And in this case, the best value for the weight and the bias is not 0, according to what we have started our here. It's just so that we can see exactly what's happening when we run our iterations with the cost. So between the left and the right here, these are the same things. It's just that the one on the left is more zoomed. The one on the left is like our first 100 iterations. And the one on the right side is all of our 10,000 iterations. So these are the same thing. It's just the one on the right side is inclusive of everything. The one on the left side is the first. The main thing here is just to know that as we proceed along this gradient descent, the size of the change for our cost as it approaches 0, as it approaches the local minimum rather, the changes each step are going to get smaller and smaller and smaller. Smaller and smaller and smaller. Let me try to see how that correlates to this. Yeah, I don't want to confuse you, so I'm just going to leave it at that. This right here is like the opposite of exponential. It's like exponential decay, I guess is maybe what you can call it. But you can see here that the cost starts up really high, like 80,000, and then it rapidly descends here as it approaches the lowest cost. And the lowest cost is going to occur when we get somewhere in the realm of like closer to our 10,000th iteration. So here, this is our 9,000, or this is our 10,000th iteration. It says 9,000, iteration 9,000. Let's just call it that. I don't want to be confusing. But this is our set that represents 10,000, because this is going to go all. Okay, so for predictions, what we're going to do is we're going to take this final weight and this final bias, and we're going to use it to make a prediction now that we can do that. And remember, for this lab, the first slide, or the first section we had up here, we were setting our training data. We only were training 1,000 square foot to $300,000 and 2,000 square feet to $500,000. We're going to introduce a new X input and make a prediction on that here, and that's what this middle line is. So we know that with our model, if we have a 1,200 square foot house, based on our model, we can make a prediction that that's going to be $340,000. Okay. And then the other thing we can do is we can depict our efficiency of our gradient descent formula. We can depict it as a contour plot here. So what this contour, like this thing, whatever that's called, they're both converging toward a line. Basically, it's showing us where our cost is and where our bias and our weight is in order to achieve that lowest cost. So for this, it's close to 200 here for our weight, and it's close to 100 here for our bias. Okay. This line here that's pointing, these arrows that are pointing towards our lowest cost, the longer these arrows are, then the higher our cost is. So further away, more cost. And this is not a straight line. It looks like it because we're zoomed out, but we'll zoom in a second here to see that it's actually not, they're not all straight, like linearly aligned. If you were watching an earlier video about the gradient descent and the cost function, and you saw I was explaining this contour plot, the contour plot is similar to, it's like if you were to take a cross section, like a flat cross section of a soup bowl plot. the further out you get from the center of these concentric ovals, these colors and these numbers represent a higher cost. So the goal is to get some weight and some bias that converge toward the center, which will be the lowest cost for whatever, you know, your model is. And this is just a zoomed in version. So like right about here in this section here, if we were to have like more delicate shapes, you would see that this is not completely straight, like a straight line. It actually looks like this, because something I was saying before is that like as your gradient descent runs, the steps become smaller and smaller and smaller as they converge towards your local or global minimum. And that's what this is representing here. Just smaller and smaller and smaller. And then the last thing that I'm going to show you here is kind of referencing back when we were talking about the learning rate, how the learning rate needs to be the right size. If it's too small, then our algorithms just be like very slow and very inefficient. If it's too large, we could overstep our local minimum, and we could actually cause it to diverge, which will just increase the cost instead of decreasing it. So we're going to play around with what happens when we have a alpha that is too large, just to see what that does. I don't think that this is necessary for you to worry about so much here, but these like little diagrams are important. So let me try to zoom in here for you. I wish that this was a little bit more delicate with the lines, but so when I was saying before divergence, right now our alpha is so large, and this is like evaluating out to like 0.08, which doesn't seem that large, but for this it is. Let me just make sure that this is what I'm telling you is the correct thing. Oh, it's 0.8. So yeah, 0.8 is too large. 0.8 is too large, so this is just causing this to render like just not great. I wonder what happened if I actually made this like ridiculously. I feel like this is good enough for now. What's key to know though is like the overstepping that's happening is causing our gradient descent to bounce over our local minimum instead of approaching it. So like if you were thinking about this as starting at the bottom here, it's going from this point to 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 this point, and it's actually increasing the cost, and it's only going to get bigger because it can't, like with the size of the alpha, it can't actually reach the deepest part of the valley. Instead of actually achieving it, it's going to just keep getting bigger and bouncing up. So just know that when you see this is probably why it's important to graphically depict this, because you'll need to be able to like see what's happening. I don't know, there's probably a programmatic way to determine the best alpha. I haven't gotten that far yet, so I don't know the answer to that, but I'm pretty sure there's probably a way to do that too. But just know that if you at least graphically depict what's going on with your costs, you'll at least be able to know whether or not you're diverging or converging. Because if you're converging, then those values are going to get smaller. If you're diverging, they're going to keep getting larger. And the first stop, if you're diverging, is to look at the size of your alpha. That's the biggest thing. Okay. So, whoo, child, I'm tired. That was a lot. And I hope that all made sense. But yeah, this is my explanation of gradient descent for linear regression. We made it through, and we're going to come back and talk about more gradient descent, linear regression stuff, but we're going to do it with multiple gradient descent and multiple linear regression, which is related but more complicated. So stay tuned for that. Expect those little stream videos to be up sometime later on this week, probably like a Thursday-ish or a Friday-ish. Somewhere around about there, I don't know exactly, but go ahead and comment, like, and subscribe, and hit that bell icon if you want to get the latest updates and know when I go live, because I do not have a schedule and I probably won't be getting one anytime soon. Sorry about that. But anyways, thanks for coming by. Appreciate your time, energy, and attention. Check the resources. I'll be continually updating the resource list with new links for free resources to help you get into your, machine learning, AI, deep learning, all that kind of thing. Jump on the gravy train. Let's go out and get this bag. Let's get these dollars, because these are some good jobs. And all it takes is a little bit of like tinkering. You know what I'm saying? You ain't got to be an expert. Learn with me. Come study with me. I'm here to help. If you have any questions, just pop them in the comments below, or come and check me out on LinkedIn. Everything you need to know about how to get in contact with me is on my link tree. Just go to LinkedIn. All my notes and everything will be posted there as well. Okay, so with that, have a great day. Keep it Gucci, keep it Prada, keep it, keep it fresh and clean. And I'll catch you on the flip side.